Uh, so I decided that I will give you more examples of power laws because on one hand, as I said, I don't want to get into mathematics, but on the other hand, this object power law, as I explained to you, it's a very fundamental concept. And it's not only in social and financial things, but also in natural things. I will have a long list of phenomena which are described by power laws. So it is one of my ambitions that even if I don't succeed to teach you much, but at least how power laws look like, I hope I will succeed to explain so many times that it will be even boring. So to remind you, the way power laws look from the point of view of without writing formulas and mathematics, is that one can have two axes, like the wealth of people and the number of people which have that wealth. And if there would be a Gaussian distribution, you would see in the middle some kind of you see, I'm going with an arrow, little arrow around there. You would see something like a bell distribution. And if it's like this, then the rule is the following: that each time I look at the wealth which is let's say 10 times bigger, then in fact the number of people having it will be 10 or 100 or 20 times less. So in a sense, it's like a pyramid because there is one person which has the most money, and there are many people which have the least money. And in the middle, they are separated by the same factor. So in this particular graph, I have chosen that each time I ask about wealth, which is 10 times more, the number of people having it will be 100 times less. So if I start with 100 million having $1, then I will have 100 million by 1 divided by 100 will be 1 million people which have 1 times 10, $10. And then I can go on and divide again by 100. And if I divide 1 million by 100, I get 10,000 people. And the wealth which I'm addressing now will be 10 times larger, will be 10 times 10, $100. And like this, I'm getting to the last one, which would be one person having 10,000. So you see that there are many rules for power laws. In particular, in previous examples, we had that the richest person had the hundreds of billions, which is more realistic, while in this example, the richest person has just $10,000. And I want to make also the contact with how people speak in general about power laws. You see, until now, I was speaking about $1, $10, and $100. But in general, people have not an integer amount of money. So there will be people which have between 1 and 10, and people which have 10 and 100. So the way we interpret this power law is when we say that there are 10,000 people having $100, which was one of the points here. What we really mean is that in this entire region around 100, let's say between $10 and $1,000, the total number of people in this region around $100 is 10,000 people. So, I wanted to correct some misunderstanding which may arise that it's in a power law, it is obligatory that people have only multiples of 10 or so money. The way I expressed until now in terms of this discrete numbers is in order to make this clear without any mathematics, because describing in terms of mathematics all these numbers in the middle would make the thing more complicated and less likely for you to follow. And in fact, I want to invite you all again to interrupt me if you don't understand, because as I said, will depend very much on understanding what is the power law, because it's about this that I will speak during this lecture and probably also a couple of other lectures which are coming. So if you want to save yourself the situation of not understanding, just listening and not understanding and being bored, you better interrupt me now. So now I give you another example to see that the different power laws can look differently. So each time I go from one wealth to another, I multiply by 100. And the number of people which are in this corresponding to a wealth which is 100 times larger would be 10 times less. So this time, if I start with 10,000 people having $1, then the next time for $100 would be 1 times 100, and the number of people which would be 10,000 divided by 10. 1,000 people having 100, and if I go again, I divide it again by 10 the number of people and multiply again the wealth. So I have a distribution of wealth, which you see is very different from the previous one, because that one ended with a richest person having $10,000, and here it's $100 million. And to make even more generic, so that you understand that, what power laws is in general, it doesn't have to be powers of 10. Here I take powers of 2, 1, 2, 4, 4, which is 2 times 2, and 4 times 2 is 8, and 8 times 2 is 16. So each time, again, the rule is that the numbers are which are equally distanced on the graph are actually differing by equal factor, which in this case is factor of 2. And on the y-axis, I have a factor of 3. So I start with 1 person, 3 persons, 9 persons, 25 persons, and 81 persons. And I can have a power law in which 81 people have $1. And according to my rule, I divide by 3, the number of people will be 27, and I multiply the wealth by 2, and the number, so the wealth is 2. So there will be 27 people having $2, and 27 divided by 3, 9 people having 2 times 2 equal $4, and 9 divided by 3 is 3 people having 4 times 2, $8, and in the end there will be 1 person which has there is a mistake. It's not 12 here, about 2. So 8 times 2, 16. So this is another example. So in general, here I can have more examples. Like for instance, here I continue to have 1, 3, 9, 27, 81, and if I multiply by 3, 243, and then again I multiply by 3, 720. So these are powers of 3. So each time that I divide by 3, I will go from one step to another here. And each time that I multiply by 2, I will go one step here. Except that now, so one possible power law would be that I divide by 3 and multiply by 4, and divide the number of people by 3 and multiply the wealth by 4. So in that case, there will be 187 people which have $4 and 729 which have $16 and so on. In all these cases, as you see, the power law looks like a straight line on this kind of graph in which the numbers are separated by the same factor rather than by the same difference. And I can have another power law in which I divide each time by the number of people by 3 whenever I multiply the wealth by 2. And in that case, I have this graph. And here I divide by 9. You see, I go 2 steps down whenever I multiply the wealth by 2. So it will be divided by 9 here when I go here. And again, I divide 729 by 9 and I get 81. And with the wealth, which is $2 times 2, 4. And in this way, I will get with just one person having $16. So you see that this way of drawing things, first of all, allows me to recognize power laws very easily because they look like straight lines. And secondly, it allows me to speak both about small numbers and about large numbers, as we had 100 millions and so on the same graph, which is on my screen, it's less than half of a meter. And if I would have equal distances for equal differences between the numbers, of course, 100 millions would need a screen of hundreds of meters. And here is another power law on the same graph, except that now I divide it by 3, but I start from 243, having $1. So, so on this kind of a graph, as I showed you in few other examples, one can plot the wealth of people. In this case, we took the numbers from there is a journal called Forbes, which is mainly about economics. And they have every year a list of the richest 400 people in the United States. So we looked for about almost 20 years, and we made the statistics, and we compared with the theoretical power law distribution. And you see they are the blue squares are the simulation results, and the red circles are the actual numbers. And as you see, the theory and the straight line, it's a power law. And as you see, both the theory and the experiments, the observations, and the power law, the ideal power law, they agree very much. And this is in spite of what you see um, in the inset, where there is the average wealth among these people. And as you remember, there was a crisis, a bubble, the dot-com bubble, which burst in 2000, and there was a drastic loss of money for all these rich people. But this didn't affect the fact that the power law was still present. So this property of wealth, of respecting a power law, it's very robust. It didn't change from since 1869 when Pareto discovered it. And in the meantime, of course, there were world wars and big crises and empires which collapsed, like the Russian Empire during the Revolution, and the German Empire collapsed, and the Turkish Empire collapsed, and the Austro-Hungarian Empire collapsed, and so there was a lot of changes, but the power law remained, which indicates that there must be some very simple and very general explanation for that. And as I'm already on the third lecture in which I'm promising you that I will explain to you that, from the experience of the other years, I am actually probably going to do that. But now I realize that I'm not anymore in the slideshow mode. Here we are. So as I told you in the previous lecture, this is true also for the number of cases. So in a sense, you can think about in terms of people. You have here the various counties in the United States, and instead of money, you have the number of people ill, or rather the number of people per capita ill in that places. And as you see, the axes are what I call logarithmic axis. But again, in terms of without, I don't have to use that name. All I have to see is that the different points which are at equal distance, they are separated by equal factor, and on the y-axis too, and therefore a straight line is what we call the power law. And that other graph, it's the same, basically the same graph at another date. This is the March 20 probably. And these are the same graph, except that for being only for the United States counties, on the left side you see different countries, and you see that again there are some countries which have a very large number of very large frequency of corona affected people, and there are very few. Sometimes, of course, the last one is just one, the biggest one. And there are very many countries which don't have any corona. I think that in this respect, in many respects, the African countries are disadvantaged. But when it comes to corona, they are apparently, many of them, advantaged because there are no big cities, and therefore people are less close to one another in great numbers, and because of this the epidemics cannot propagate so well. So this kind of countries with for tropical forest and or desert, they will have less corona cases, and there are quite a number of them. So now there is a series of other examples. I'm not going to explain them. It's more. In fact, I feel guilty for myself because my objective is to get us as fast as possible to this explanation, which I promised to you about how power laws may appear. But on the other hand, I feel kind of obliged to take the opportunity to let you know about the generic cases. Yes, I see that somebody raised the hand. Rebecca Meller, do you want to say something? Rebecca? Yeah, there is another person which raised the hand. Is it by chance or somebody?
No, I raised my hand. Just that last comment that you made, I think, was very important about how African countries are less affected because they live in smaller communities. I think that that's the proof of the Pareto principle, more than all of these graphs, because the Pareto principle basically tells you that the more wealth you have, the greater access you have to expand that wealth in a disproportionate manner, right?
Yes.
So that if I'm living in a city, I have access to so many more people. So
yes, exactly. Yes, absolutely. So indeed, this is the basic rule of capitalism, that if you invest something, then you can gain. If you invest twice as much into something, then you will gain twice as much. So if you put your money in some equity, in some shares, and the shares go by 10%, then if you invested $100, you get $10, and if you invested $200, you get 20. So yes, this is a mechanism. Of course, you can also lose if the shares go 10% lower. Then if you invested 100, you lose $10, and if you invested 200, you lose $28. So
right, but if I had $100 to invest, and without it affecting me, but then somebody else had $10,000 to invest without affecting him, it doesn't really matter how much you're losing or gaining at that point, because if you had the money liquid, then it doesn't matter if you're losing it. What's more important is when you're gaining.
Yes. For me and you, might be not so important. If it is liquid money which we don't use, then we don't mind so much to lose them. But we are. I don't think that we are generic. From what I can imagine, there are some people which connect their self-appreciation with how much money they win, and therefore they will have a different.
You're saying it's an identity. It's an identity crisis. You're saying.
But I'm very happy you said that, because basically this means that you will follow very well my explanation of the appearance of power laws. What you said in words, I will say in pictures, because I promised there will be no mathematics, but basically that would be the point. And the same thing is with the other things, like for instance, the number of species versus the number of individuals which that species has. So there are, it's exactly the same thing. Like if you have a species which have 1,000 representatives in a place, and if it is good conditions for them, then they will multiply it to, let's say, 2,000. While if there are 10,000 and they are there is enough food and conditions for them, then they will, if each of them makes a copy of itself, then there will be 20,000. So the same mechanism which you just explained in terms of money and of epidemics. It's also true for the number of individuals in a population. So it's not a wonder that one also gets a power law for that. And also the number of species at a given time, because species in general, new species appear because one species branches into species. So again, there is this situation. In terms of craters on the moon, we also get a power law, which is very impressive because it goes from 10 kilometers to tens of meters, and it's a power law for all this range. And this is actually related with the fact that the craters on the moon are the signs which meteorites leave when they hit the moon, and here is the scale for the meteorites, in which there are some of them which have 10 kilometers, and there are many of them which have just millimeters, and they are all of them very well described by power law, in the sense that there are many small. And here, Dina, here it's a little bit the opposite. If you have a meteorite and if he cracks, it gives the rise to two meteorites, which is each of them about half of their size. So here, in place of multiplying the size, the number of the size is going down, but the number is going up. So it's in a sense the opposite, but the same principle. Okay.
I understand.
So out of a meteorite which is 2 kilometers long, you can get two meteorites which are.
It's like cell division. It's like when cells divide.
Yes.
Same
Except
idea.
that here the meteorites don't grow. The ones which are smaller, if you have one meteorite which has 1 millimeter and it breaks, then it breaks into very small ones. So there are very many examples. Let me see if there are more. The one which I spoke a little bit last time, but I didn't insist, is I'm trying all the time to make contact with things which you already know. So in the case of earthquakes, even before anybody told you that it's a power law, everybody knew that when you speak about earthquake of size 6 and about earthquake of size 5, the one which is of size 5 is not just by a factor of 1/6 less than the 6th one. It's by an entire order of magnitude. It's 10 times less. The Richter scale he invented exactly because the earthquakes can be very small and can be extremely large. And of course, the very small ones, which we don't even feel, the ones which are of size 1, 2, and I think that even 3, there are very many, but we don't feel them. The ones which are of size 8, fortunately, we didn't see it here, but in California, something like 15, 20 years ago, there was a very large earthquake, which was of size 8. But these are very rare. So again, the power law just explains this kind of things, that the different sizes of the earthquakes are separated on the Richter scale by equal factors, not by equal differences. And there are many other things, like the number of products versus the number of product type as a function of the number of products. So an example would be that if you compare toothpicks, the number of toothpicks with the number of cars, or planes which are sold, then the number of planes is relatively small, while the number of toothpicks is very, very large. This is an example of that. The typical thing is the number of treatments versus the number of patients which have that treatment. There are people which are very healthy and young and healthy, and they don't need any treatment, and there are quite many of them. And there are people which are so ill that they need every 2 weeks treatment. Unfortunately, that was the situation with my mother. Every 2 weeks we had to bring her to Hadassah. So I was very much aware of this fact that the number of patients which have a certain number of treatments goes like a power law, in the sense that there are very many people which need very little treatments, and but there are a few people which need a lot of treatments, and this also is in terms of the cost. So as I told you at the beginning of the course, the 20/80 rule is very many times invoked in this context, that for Kupat Cholim, it is important that to know for them that 80% of the expenses of the Kupat Cholim goes for 20% of the patients. So as you see, the inequality exists not only for good things, but also for bad things.
I think that a good example of it is also Facebook, especially with what's going on now in the news. You can see the power law with Facebook in the negative way, in the sense that normally the power law would show that that when a community is in an ideal situation where it's going to thrive, right, it'll constantly expand, right?
Yes.
But an example like Facebook, I guess, would be the opposite, where it's feeding into an innate insecurity in people. So in the end, it's the 20% that's on Facebook that's dictating to the rest of the world what is basically what the standard is, right? And that's feeding into an insecurity of the rest of the world that they're not living up.
I agree that many of us about 20 years ago, when all this globalization of communication took place, we were hopeful that this would encourage democracy, because we said, okay, now everybody has access to express oneself. Unfortunately, as we see, the technology is misused in many situations. In particular, it appears that in Facebook there is this tendency of encouraging confrontation, because this makes people which make this confrontation to use more intensively the platform, and therefore they make more money. And of course, there is also the fact that people which have invest less time in constructive things have more time to invest into quarreling over the internet. David Hakohen, I see that there is a hand raised. You raised the hand.
Can you hear me?
Yes.
Can I ask in Hebrew? It's okay?
Yes. But please remind me after I answer you in Hebrew that to switch back to English, because I have a tendency to, continue in the language.
אוקיי.
Okay.
רציתי לשאול, מה היחס בדיוק בין חוק החזקות, ה-power law, לבין ההתפלגות פרטו? זה אותו דבר או שזה קשור? אני לא הצלחתי להבין את הקשר ביניהם, את היחס.
Power law and Pareto law are basically the same thing, except that when Pareto found the first power law, he found it in the context of wealth distribution, actually income distribution. And because of this, in the strict sense, at least at the beginning when he discovered it, it was about wealth. After that, people started to discover that that power law, the same kind of power law, exists for other things. For instance, one of the things which the first thing that they discovered is that if you look in a text, if you choose a text by random, actually at the beginning they have chosen Moby Dick, and then you count how many times each word appears, and then you make a graph in which a word which appears 10,000 times, how many words appear 10,000 times, and how many words appear 1,000 times, and how many words appear only once, and they got a power law. And they still called it a Pareto law, even though some people call it nowadays a zip law. Zip was another scientist which was interested in power laws. So for any purpose, if you use the word Pareto for a power law, that would be correct.
Okay, thank you very much. And another question connected to it, can you explain, for example, the number of languages versus number of speakers? I see in the...
It's very easy, because the number of people in general are speaking the language which their parents have spoken. So it's the same mechanism which Dina spoke about. If you have 1,000 people which speak, for instance, nowadays, unfortunately, Aramaic, there are very few people left which speak Aramaic, but there are, by the way. And many of them, they are in Israel because they came from Kurdistan, and this is where Aramaic was still spoken until the last generation. So now, unfortunately, this is a bad example, because even though the parents spoke Aramaic, the children probably spoke Hebrew because they wanted to understand what their friends at the school speak. But in general, you would have a situation in which the children of a certain population speak the same language with their parents. Again, it's not always true. For instance, my parents spoke Romanian, and I tried to speak Hebrew. But by the way, I speak a lot of English too, as you say. And but in general, especially traditionally, if you had parents which spoke German, then their children would speak German. Therefore, the same kind of rule which says that if you have 10,000 people speaking language, then and if they multiply in one generation by giving birth to another 20,000, then now you have 30,000 people speaking that language. So this is a very similar mechanism with people getting richer or with other examples.
Thank you.
But the distribution is it's opposite. It's like from the left to the right. No?
Say it again.
The distribution itself. I said in Hebrew. Okay, it's easy for me. זה נשמע שפה אבל ההתפלגות תהיה חיובית, כי יש קצת אנשים שמדברים סליחה, לא, יש הרבה שפות שקצת...
No, it's actually, there are many languages like Aramaic now. I think that Aramaic, the linguists are in a race of trying to make interviews with the last people who speak Aramaic, because in one generation there will be nobody left to teach the linguist what the language is. And of course, each of these languages is important. There are many languages in the Amazon in which there are tribes which are shrinking a lot, and so there are very many languages which have a very small number of speakers, and there are languages like Spanish and Chinese which are spoken by billions of people.
Okay, thank you.
Even though it's difficult to say Chinese, because from where we look, it looks like all the Chinese speak the same thing, but in reality, they speak quite different languages. The luck is that, how should I say, even if a word is pronounced very differently in two Chinese languages, they use the same sign for expressing it. And because of this, if somebody from north of China visits south of China, if he speaks in terms of by mouth, they don't understand him at all. But if he writes, then they understand, because it's the same sign. So I'm not sure whether one should count Chinese as a single language. And the same situation is with India. They are very, very different languages. In fact, not only there are hundreds of languages, but there are two families of languages there which they don't have the same origin. They are completely different. The northern half of India speaks a language which is very much similar to, not very much, but somewhat similar to the European languages. And the south of India speak a language which was spoken in the Middle East before probably at the time of the Sumerians or something like that. But this is not clear. Anyway.
The fact is that they're not going to teach that dialect or whatever in university, whereas so the fact is that they're not going to teach those dialects in university. They're going to teach Asian studies, or they're going to teach Mandarin or whatever it is, because of the amount of power that those people who speak that language have. And that's another example of the power principle, the idea that it's going to spread over to other countries and become part of the curriculum or part of whatever.
You are right, but this is not specific only to China. And of course, now the Chinese government became, in our minds, identified with forcefulness but this kind of centralization of the national language happened in most of the countries. For instance, in Italy, to this very day, there are local dialects which barely can understand one another. But the schooling system forced the Florentine dialect as the national language. And now most of the Italians just speak that language, maybe in addition to their local language, which sometimes might be very, very different. And the same kind of centralization of the language happened in most of the other European countries. In France, in Germany, they had very different dialects, and the kind of political pressure to have a central power enforced the emergence of a single language. And this might happen eventually in China. What happened in India was that some of the minority languages when the government wanted a few tens of years ago to enforce the dialects which are based on Sanskrit, which are from the north, as the national language, the people from the south, they are called Tamils, which had a very different languages. They opposed it very much. And then the compromise was that now English, it's one of the national recognized national languages in India, and most of the Indians, when they meet outside India, they have to speak among themselves in English because they don't know the language of one another. In any case, I think that we spent enough on languages, though it's for me, it's a very interesting subject, but it's not what I'm supposed to teach. Another very famous law is that if you ask how many towns have a certain population, then you would find that let's say there is one city with 10 million people, and then there are a few towns with 1 million, and then are even much more with hundreds of million, and you get a power law. Incidentally, this is how ZIP got. As I told you, there was another scientist after Pareto, which retook this idea of power laws. And at the time that he was, Austria was small because it was after the First World War, and it became a very small country, but it had a very big capital, Vienna, because a few years before, when there was an entire empire, Austro-Hungarian Empire, Vienna was the capital of that empire. So Vienna was disproportionately large for the size of the country and of the other towns in Austria. On the other hand, Berlin, which was the capital of Germany, was a relatively small town because Germany unified relatively late. So the country was very big, but Berlin didn't yet have time to develop. So in both countries, the power law wasn't really perfect. And ZIP observed that if the two countries would unite, then the power law would be quite perfect. So he became a partisan of unifying Germany with Austria, which at the time was identified with the fascist, with the Nazi ideology. So he got the wrong side of history, and he was kind of discredited. But in any case, in most of the countries, this power law for the size of cities, it's fulfilled quite exactly. Okay, so then there is an entire list of other things. Like, of course, after explaining that this power law is related with multiplication, then you would not be surprised that the number of religious other people, like how many people, how many religions have a certain number of people. So there are large religions like Catholicism and Islam, and which are very large, and there are some other religions. I don't know, some tribe in Papua, which maybe they believe in something, and there are 200 people there. Actually, there is how is it called? there is a sect Karaim which are somewhat Jews, but they were separated in the 7th century, and they are of this example that in place of getting larger and larger, they get smaller and smaller. That would be an example of religions with a very small number of adherents. But again, typically the religion of people are inherited from their parents, so it has the same mechanism like money, that like capital, that if you invest, then you can get more. And of course, the distribution of family names is the same. And there are very many other things. The last one I see the drugs. So I suppose that if somebody takes something against headaches and it likes it, then it recommends it to his friends. So this is how you have a similar multiplication of the number of people taking a certain drug. And another example I see here, innovations. Of course, if somebody makes an innovation, then people around him would be, or her, would be encouraged to make new innovations, maybe based on the innovation which that person did. So again, the number of innovations in cities, it's also power law. And of course, the extreme example is the Silicon Valley, in which they have more inventions than anybody else in the world. And I suppose we are the second, the startup nation with a lot of inventions too. And the bankruptcy of firms. If a firm bankrupts, then the firms which are providers to that firm have a chance to fail too, because now they don't have that client, and so it's a similar situation. And I promised to you that this is also this kind of power laws. It's true not only for earthquakes, but for many other things like fires. There was an extremely large fire in Australia some 3 months ago, in which hundreds of people have died. And also in California, there is periodically fires. So there are typically hundreds of people. And in last year, there was in Sudan and Egypt, there was like hundreds of people dying in floods. And there were these hurricanes. Now, and there was a Katrina with 1,000 dead some 15 years ago. But I wanted to say that this kind of disasters are usually associated with the climate change. But the power law actually existed long before, and there are cases in history with much larger disasters. For instance, there were in 1362, there was a very large kind of hurricane. In Europe, they are not called hurricane, kind of tempest like this, which affected both Holland and England and part of Belgium. Even though it's so long ago, they were able to document at least 100,000 dead. And there is something much closer to us. In 31, in central China, there was a flood with the Yangtze River, which essentially changed its course. So they counted something like 3,700,000 dead, plus something like 53 million which were displaced by the flood. And you see here there are many other examples from the history. It's difficult to say that these are due to a particular cause or another. They are just results of this power law. Of course, there are not many with 3 million dead. That's exactly the point. That there was, for what I know, there is only one example in the history. However, this kind of very big floods did exist during the prehistory, because here, for instance, there are the different colors here show what was the Earth, the non-sea, during this light green is 16,000 years ago. This a little bit darker green was 8,000 years ago, and this dark green was 7,000 years ago. 7,000 years ago looks like very far away, but it was already at the time that people discovered agriculture. And in fact, because there was earth between France and Britain, the agriculture could reach the English islands during that time. And another example is the Bering Sea, which again at that time it was Earth until the climate became more hot, and then the glaciers thawed and became water, and then the level of the water raised until today, where Alaska and Russia are separated by this strait. But about 7,000 years ago, actually, they were united. And in fact, this is how Homo sapiens, how our species got into America by this strait. Incidentally, the Bering Sea became famous because in the Russian encyclopedia, for a while, there was a very long article about one of their leaders, Beria. But then they declared him to be a criminal, and they took out the article of Beria from the encyclopedia, but they have to keep the number of pages of the other articles. So they had to fill that many pages which were about Beria with something which was Bering Sea, because it was just before him in the encyclopedia. So, for instance, the kibbutzim in Israel, they were very left wing at the time, and they did what Stalin said. So they got a letter that they have to substitute the article about Beria with an article about the Bering Sea. In any case, as you see, there were very extreme floods which involved very large things. In particular, here it is the situation in the Gulf, which the Persians call the Persian Gulf, and I think that the Arabs call the Arab Gulf. In any case, that Gulf about 10,000 years ago, or a little bit more, when there was a glacier era, so much of the water was in the glaciers. This was Earth, and when the climate got hotter, then the water from the Indian Ocean started to enter there, and it was pretty fast. I think that it advanced with about 100 meters per day or something like that. So the people which were living there, they had to go north, and it might be that this is the origin of the story of the Mabul, of the of Noah story. And of course, at that time, there were nobody to stop this global heating, because Greta wasn't there at the time. So there I think that I convinced you in this lecture that there are very many examples in which, due to this kind of phenomena, which they are called autocatalytic, in the sense that the very presence of the phenomenon catalyzes, encourages that phenomenon to become larger. So this happens with populations, and with the capital, and with diseases, and with so many other things. And this is what we are going to try to understand, to understand how it happens, why it happens, and what are the consequences of this happening. Before I go to this other things, I want to show to you another graph, which is again related with this guy Zip, in which he paid attention that the power law looks like a power law even in the opposite direction. I think that one of you mentioned that one could do the opposite. Like here, at the time, the Walton family, the guys from Walmart, they had the largest wealth in the world. It was 90 billions. At that time, 90 billion was the largest. Nowadays, we have crypto with 200 billion. And Gates was the second at the time with 48 billion. And what is this? Buffett was number 3 with 41. So if you put them again on a logarithmic scale, on the kind of scale in which we were discussing, in which the numbers are separated not by their difference but by their factors. So for instance, the difference between 1 and 2 is larger than between 2 and 3, but it's basically equal with the distance between 2 and 4. And these are the height are again by equal differences mean equal factor. So you still get a straight line on such a graph. So I'm bringing this to your knowledge because it might be that sometimes you will see this way of expressing power law, not in terms of how many people have a certain wealth, but what is the wealth of the first, and what is the wealth of the second, and what is the wealth of the third, and so on. It can be proven, but of course I will not prove to you that if you get a power law with the first kind of graphs, which says how many people have 1 million and how many people have 10 million, then you also get the power law by asking how much wealth has the first and how much wealth has the second and how much wealth has the third and so on. And here it is the graph, and again with Walmart's, because Walton died at some stage, so his wealth was divided between his 4 children and the wife. So then they went to each of them to much lower. But basically that was Walmart, Gates, Buffett, Allen, Dell, and so on. I think that I finished with this. Before I go to the next presentation, please tell me if there are things which you would like to ask about what we spoke until now. Here I'm.
I'd like to ask a question if you can hear me.
Say it again.
Hi, can you hear me?
Yes.
So I wanted to know,
Yes.
yes, so I just wanted to know if you could explain just the basic definition of the power law. We looked at a bunch of different examples as to sort of how this works, but really in just sort of the bare minimum sentence or two, how would you define it?
Okay, so maybe I will, in spite of the fact that I promised that I will not write formula, I will write a formula because it's very simple after all. So the number of people having a certain wealth and number of people of a certain wealth, W, is proportional to 1 over W to some power, P, let's go. In order to avoid writing this formula, in my opinion, let me also write it properly, superscript. So in the case, in the cases, like for instance here, it would be that n of W is 1 over W to the power 2, because you see that if W is 10 times more, then the number of with that power is 100 times less. So in general, the formula is that the number of people having a certain wealth is equal to 1 over the wealth at some power, which I most of the time I took it 1 in order for you not to get confused. And in order also in order to avoid problems, I found another way to say it, that for W going to K times W, one get N going to N over L, where K and L can be anything. So essentially, what I was showing by examples of the time, because I didn't want to write formula and I didn't want to confuse you, is that if I systematically, whenever I multiply the wealth and I ask about that wealth, how many people have that wealth, the number of people will be the number of people which before divided by some number. So these two numbers, K and L, can be anything. But saying this, what the first line says is essentially saying this formula that the number of people having a certain wealth is an inverse power of the wealth. Who asked this, Dina?
No, I did.
It was Rebecca who asked that.
Question.
Anyway, did I confuse you more by these explanations, or
no, you actually clarified. Thank you very much.
Okay, good. So let's go to the next presentation. Save. Okay, just a second. It takes some. Okay. Okay, so now I'm a little bit, how should I say? In any case, it's close to 2 hours, and I don't want to start with something heavy. So I'm now in this slides. I have to share it. Just a second. Share screen. Okay. Is it now shared? Can you see the screen? Rebecca?
Yes, we can see it.
Okay. So now I will make the contact between the power law of the wealth of people and the market crashes. It's again in terms of motivation, and it will what I will speak after I finish with this bracket, so to speak. I will not depend very much on this 20 minutes, which I intend to devote to the market crashes. But as I said, I want to motivate, if it is still necessary, why we are so much interested in power laws and in how they appear. Now, I see that Dina has the hand raised. Is it from before, or is it something new which you want to say? It's probably from before. So what it becomes now important is that having these power laws means that the average are not so important. For instance, if somebody asks what is the average size of an earthquake in California, then one would get probably something very small, because as I said, there are many, every second there are of size 1, and every day maybe of size 2, and every week of size 3, and they are going almost unobserved. However, the real important one was the one which had almost size 9, and which I remember it destroyed the main bridge in next to San Francisco, and it affected also very much probably the Silicon Valley, which is in the same region. So, so in the same sense, what is important in the economics life and in general in the life of social life is less what is the average, let's say, how many failures are of middle-sized companies. And what is more important is, as you remember, the Enron scandal in which very many billions were involved, and the Lehman Brothers collapse, which was essentially the signal for the depression in 2008. So what is really important are the big players in the market and not the average. And this is actually important because many people think that for scientists it's important to compute averages. In fact, I remember that there was a joke that what is a statistician? Statistician is somebody which would feel comfortable if you put his head in the oven and his legs in the refrigerator, because his average temperature will be optimal. You know, very hot and with very cold. If you make the average, then it looks okay. But of course, for a human being, it's not okay to have his head in the oven. In the same sense, the difference between Gaussian and the actual fluctuations in the stock market are very, if you look with the naked eyes, they are very small, they are in the tail. So there is this difference in which the probability of having an extreme fall, an extreme negative value of the fluctuations of the market is basically zero according to this line, to the narrow line, which is the normal distribution. But it is not so zero. It can happen, let's say, every 10 years or 20 years, as opposed to the Gaussian, which you know might be a good approximation for quite a number of times. And however, if this happens, then essentially this can be very serious, the beginning of very serious crisis, like the one in 2008, or even worse, like the one in 1029. So the question is how this kind of things can appear. And what would be the consequences of it? For instance, in the 90s, there was a formula which Black-Scholes have computed, which was essentially how much a measure of the risk which you take by making a certain contract about a certain equity, about menaya, share in English. And they assumed that the fluctuations, the risk of this getting very much or getting very low, it follows a normal distribution. And they even got the Nobel Prize for that formula. And because of this, one of them was died actually before, but the second one, I think that Scholz made capital management fund based on this formula, And he even brought other Nobel Prize winners into this company. And he invested. People gave them money to invest according to their wisdom. And at a certain stage, this kind of difference between their assumption that everything is Gaussian and the reality clashed. And their fund lost almost 5 billion, which at the time was really much more than nowadays. It's 5 billion, and basically their company went bankrupt. It was saved by being bought by some other company, which I don't remember what it is. The financial crisis in 2008 was also related with an underestimation of what can be the collapse of real estate prices. So the question is how this could happen. And the relation with what we spoke is the following. And I take this, as I said, all these 20 minutes at the end of this lecture. If you don't understand, it's not a disaster for the rest of the course, because I will not depend on it. But it is important, first of all, because of this importance in the way the crisis take place, but also it's mathematics, so to speak, in terms of your general culture in mathematics. It's important. Why? Because these fluctuations in the market are the sum of the changes in the participants in the market. So, because after all, what is the value of the market? It's the value of the capital is the sum of the value of the market which is the index of that day, is the sum of all the participants in the market. So now the point is that the sum of Gaussian distributed quantities has a Gaussian distribution by itself. Let me explain in which respect. You remember that we had this distribution for throwing one dice, or throwing 2 dice and throwing 3 dice and so on. Now the point is that, and continue to ask what happens if. Oh, I'm sorry, I didn't stop the recording. Okay. The point is that if I ask not about the sum of 3 dice or 2 dice or about 1 dice, but about their sum, as you see, their sum, it's here 6 dice, and they get even closer to a Gaussian distribution. So one property of the Gaussian distribution is that if you take quantities, which each of them has a Gaussian distribution, and you ask what is the distribution of values, or the probabilities of values for the sum of that quantities, it's a Gaussian distribution too. So for instance, you have 1 dice which have non-Gaussian distribution. But if you take more and more dices and you throw and you ask about their sum, that converts to a Gaussian distribution. So because of this, they if people were assuming that what is that? Okay, there was a signal appearing. The point is that if you assume that the distribution of wealth is Gaussian, or even flat, like it was with this distribution of numbers of a dice, if it is a distribution which is not very doesn't go to very large values, then you get a Gaussian distribution for the fluctuations of their sum, which is the value of the market, of the index of the market. So the fluctuations of the market would be Gaussian. However, if you have a power law, especially a power law which have what is called a fat tail, which means that very large values are have a non-zero probability, as we have seen that there are such power laws, then when you take the sum, is not anymore a Gaussian distribution. Now, for people which don't know much of the Gaussian distribution, this is not a surprise because you didn't have any preconceptions about a Gaussian distribution. However, people which know something about Gaussian distribution, they know that almost any sum of distributions, even if they are not Gaussian, if you put them together, you'll get a Gaussian. This is called the central limit theorem. And it's almost taken like that it's for sure like that for any distributions. And the greatness of Paul Levy at the beginning of the previous century is that he said, no, if you have power distributions, if you make their sum, then their distribution will not be a Gaussian. So the explanation, I'm giving now the very fast explanation. You can interrupt me if you think that, if you don't understand. However, I assure you already now that even if you don't understand, it will not affect the next lectures. So this is, so to speak, supplementary material. The point is that the Gaussian distribution is if you take small quantities and you put them together, then some of them will be smaller, some will be bigger, and the probability to have all of them in one direction is very, very small. And it's like throwing all the time head many times. The probability to throw heads and to get a head or the other and getting 100 times head, it's negligible. However, if you have a power law, then it's enough that in order to get very large value, it's enough that you get one single time that you get one of these very large values, which the power law allows to appear rarely, but not impossible, as it is the case with Gaussian distribution. So in the end, the point is that a Levy distribution, a distribution in which the steps are not equally sized or not Gaussian, but distributed by a power law, will have a non-zero contribution for values which are essentially have the same distribution as the distribution, probability distribution as the power law itself. So the probability to get very, very far away from the when you started is more or less the probability of having one step which got you there by a power law, which by a Gaussian you don't. That probability is zero. So the two distributions are very different. Here is a logarithmic scale, and this is a Gaussian distribution, or on a logarithmic scale, the Gaussian distribution ends much more abruptly than the bell shape. But it's the same shape, just on a different graph because of this. And this is the Levy distribution. And these are the experimental data from the actual fluctuations of the market. And this is from simulations. And as you see, both the simulations, according to the model of having distribution of power laws for the individual participants, and the theoretical distribution, and the formula of Paul Levy are falling on the same line. So this is the reality, and this is the theory of reality, which is this distribution based on power law. And this is what is a Gaussian distribution, which clearly is not correct for this particular application. As I said, normal distribution is true for many other things, but not for the fluctuations of the market. And so this kind of number in which you have 20% fall into the market would be, according to the Gaussian distribution, impossible, according to this line, this interrupted line. But according to the reality and according to the Levy distribution, this has a certain probability. Not every day, not every week, but maybe not even every year, but every 10 years, and often enough to make the life of many people very problematic. So the fluctuations would look for a Gaussian. It's here is not really for a Gaussian. It's a little bit even more fluctuating than a Gaussian, but more or less looks like this, a Gaussian, with a lot of fluctuations, but without crashes. While for this kind of distribution, if you allow the steps to have this distribution, then from time to time you have this kind of very large force. Of course, from time to time you also have very large increase. But this is the result of the fact that the participants in the market, some of them are very big. So basically, this kind of single step in which you have that much of a crash, it's like Lehman Brothers fall. Lehman Brothers fall, the entire markets fall because they are so much a large part of the market, and you have this kind of behavior of the market price, as opposed to this one in which there are which is close to the Gaussian, and which there are no big surprises. So these are the crashes which are possible for different values of the distribution. And this alpha is essentially related with this coefficients K and L, how much there is, how much the number of people changes when you change the wealth. So if there is not so much fall in the number of people which have very large wealth, then you would have for 10 billion people, you will have 100 billion in size of the wealth of that person. And if that person loses in one day even 1% of their value, let's say because news about Facebook and things like that, then 1% of 100 billions is already 1 billion fall in the market, which is a rather significant change. So the way the fluctuations grow in time for the Gaussian, they grow in a way that as time goes, you expand not that much with a speed which is less than the time. While for this kind of distributions, for Levy distribution, you might have a situation in which, as time passes, the divergence of the market, the fluctuations of the market become more and more serious, and the market becomes unstable. So in this respect, we I think that we are at the end. In this respect, we made a formula which related the inequality exponent, the Pareto exponent, the size of the inequality with the stability of the market. And we said, look, if you have inequality, you will have also instability, larger instability of the market. So, so having inequality is not good for the capitalist either, not only for the poor. And this formula was verified by Moshe Levy. Is not related with this Paul Levy from France. Moshe Levy was a PhD student of mine, and we made this, and he made this measurement both for the markets in United States and the United Kingdom, in France, and indeed he found that indeed we are right, and that the number which expresses the instability of the market is proportional to the number which expresses the inequality in the wealth of the people which are involved in that economy. So these are the actual numbers, and this is already 2 and 3 minutes. So I'm stopping here, but I kind of wanted to show to you the importance of it, and also the relation which we found to between the Pareto law, the inequality in wealth, and between the instability in the market, and the fact that in economics in general, people are arguing all the time, and none of them really can prove the others wrong. And in these examples, because we came from natural sciences, in which this comparison with the reality, you have a theory, it might be wrong or it might be good, but it's not according to how convincing you are in terms of words, but in terms of how does this reflect the actual empirical reality as measured by the experiment. So this makes this course a little bit special, because in humanities in general, the argumentation is in terms of you know, one says something and the other says something else, and you can believe somebody or somebody else according to how convincing they are. While in natural sciences, we have an objective criterion, which is how much what you say is confirmed by the empirical observations. I'm finished here, and I would like you to ask me questions. Are there questions? Okay, in this case, I thank you very much, and I hope that starting next time we'll be much more focused. Rather than stories, I will have a coherent explanation of all the things which we discussed until now. Bye.